Hey there, my name is Kelsey Parker. I am about to do homework 3 for semiconductors. I am taking it at the University of South Florida, and it's on MOS capacitors. So let's get started. So we were given the problem right here. It says a MOS capacitor is made of a P+ polysilicon at the gate, and it's 10 nanometers in thickness, and it's an N-type silicon semiconductor with ND equal to 10 to the 15th centimeters to the -3. And it also says to assume that T is equal to 300 degrees Kelvin, which means that it is at room temperature. So for part A, they asked to find the C oxide. C oxide is just the capacitance of the oxide, which is equal to the permittivity of the oxide over the thickness of the oxide. The permittivity of the oxide is just 3.9 times 8.85 times 10 to the -14th, and it's in 10 nanometers, and we want to convert it to centimeters, which would just be 10 to the 10th, or 10 times 10 to the -7 centimeters. Plugging that in, we end up getting 3.45 times 10 to the -7 farads over centimeters squared. Part B, they're asking for the work function for an N-type, which the equation would be V terminal times the natural log of ND over NI. ND was given to us in the problem, and NI is a constant because it's N intrinsic, so it will always be 10 to the 10th. V terminal is just KT over E, which will also be a constant since it is at 300 degrees Kelvin. So it will just be 0.0259 volts. Plugging it in, we end up getting 0.298 volts. For part C, they're asking for the work function of a semiconductor. The work function of a semiconductor is this equation here. You cancel the E's, and you just get 2 times the work function of f of n, which we found in part B. So you plug that in, and you get 0.596 volts. As we continue, part D is asking for the maximum depletion width. The maximum depletion width will be this huge equation here, and plugging everything in, it becomes quite simple. E of S is the permittivity in a semiconductor, and that changes a little bit from what we did earlier, because now this number here will be 11.7 since it's in a semiconductor instead of the oxide. And so we already got the work function of f of n, and we were given ND. So we can just plug it in already, and we get 8.66 times 10 to the -5th centimeters. In part E, they're asking for the work function metal semiconductor difference. And in the book, there's a figure 10.16 that we can base this number off of. And since it's at 10 to the 15th doping level for a P+ poly N-type silicon, we can conclude that the work function MS is equal to 0.95 volts. Part F is asking for the flat band voltage, and it's saying that the total trapped charge density in the oxide is 10 to the -7th. This is the equation, and now since we have this, which we found in part E, and we have C oxide, which we found in part A, we can just plug it in, and it gets 0.66 volts. Going right along, part G is the threshold voltage that they are asking for. And the only thing that we have not solved for yet is this Q prime SD max. To get that, we say the charge times ND times the depletion width, which we have all those numbers, so we can just plug it in. And then we also have found the flat band voltage in the work function of f of n, so we can just plug that in, and it rounds to 1.3 volts. In part H, they asked to draw the band diagram for VG equals V threshold. And this part is the metal, this part is the oxide, and this part is the semiconductor. So right here we have the conduction band, right here we have the valence band, here's the E of Fi and the E of F. This right here where the band bending is the depletion width. Right here is the work function of the semiconductor, and right here is the work function of an N-type. I hope you liked this video, and I hope you have a great day.